This is multivariable calculus, and in this video, I'm going to talk about section 16.3, the fundamental theorem for line integrals. So before we jump into fundamental theorem for line integrals, it probably makes sense to just quickly review what we talked about with the fundamental theorem of calculus that we learned in AP Calculus AB and BC, which was when we were integrating the derivative of a function. We could do any antiderivative at the upper limit minus any antiderivative at the lower limit, provided that the derivative was continuous. So the main idea was when we did that type of integration, we were getting the net change in whatever that derivative was measuring the rate of. Okay, so we're going to use that same idea now looking at this in the form of vector functions. Okay, so we can always think of our gradient of our function sort of like the derivative of the function when we were working in the two-dimensional space. And using that idea, you can see that if we were to go through and integrate the gradient of our function, then what we're doing is we're essentially taking the original function at the upper limit minus the original function at the lower limit. So it's got some slightly different notation because we're dealing with vector functions, but the general premise of the fundamental theorem is still the same, whether we're dealing with line integrals or whether we're just dealing with simple integrals like we were doing back in BC calculus. All right, let's take a look at an example of this. So it says the force field yi plus xj is conservative, which depends only on the position of the object. We'll talk a little bit more about that later, since it is the gradient of phi of xy is equal to xy. And so kind of think about what that means. So if this were my function, xy, if I took the derivative with respect to x, I would get y. If I took the derivative of that function with respect to y, I would get x. And I'm thinking about partial derivatives here. So you can see how that force field is essentially going to be the gradient of that function phi. So knowing that to be the case, I can solve this out in a very easy way, right? So in this case, the gradient of my original function is equal to yx. Okay, so when I'm solving out this integral then, all I'm going to do is say, okay, I'm integrating from 0, 0 to 1, 1. And I've got this f dot dr. That's going to be the same as, now I'm thinking about antiderivatives, right? So my force field, I can think about the antiderivative of it is essentially this phi function. So it would be phi evaluated at 1, 1 minus phi evaluated at 0, 0. 1, 1 plugged into xy gives me 1. 0, 0 plugged into xy gives me 0. So in the end, we just get a value of 1. So we're sort of doing the same thing that we did before when we were doing the fundamental theorem of calculus, now applying that to the fundamental theorem of line integrals. Okay, so we're going to get into some new terminology here as we go through some of these things. And one of the things we're going to talk about is called independence of path. Okay, so for the independence of path, the idea here is that if I'm evaluating a line integral and I'm going from some starting point to some ending point through my vector field, it doesn't matter what path that I take, the line integral is going to give me the exact same result. So any path that I take. And so an example of that is down here. You can see we've got this vector field and we're taking different paths through the vector field. If we have an independence of path, then I'm going to get the same line integral value regardless of the path that I take. And the way that we can check for that is if we were to complete a closed path C within our domain, then we should always get a line integral value of 0. If we can take a line integral of a closed path and we don't get 0, then we don't have independence of path. But for the majority of the questions that we're going to look at, we will have independence of path. We'll talk a little bit more about the specifics of that when we look at another example a little bit later on. Okay, so the idea here then is that when we are solving these out, we're essentially using that fundamental theorem of line integrals. And the starting point and the ending point are the only thing that are really going to matter. So let's take a look at an example of this. So we're going to use this force field yi plus xj again. And what we want to do is find the value of this work integral. So before, when we solved this, we just sort of solved it as kind of a general line integral. Well, now let's think of it as a work integral. So we're doing essentially force dotted with our distance, right? So then we're going to add up all the pieces. That's going to give us the amount of work that's done. So what this is telling us is essentially the amount of work is going to be the same regardless of the path that we take, as long as we have the same starting point and same ending point. So we're going to do this in 3 different ways. So the first way we're going to do this, we're going to take a line segment, y equals x from 0, 0 to 1, 1. So we're just going to go essentially in a straight line there. So what I need to do is I need to model this parametrically. So I can think of x being equal to t and y being equal to t, giving me essentially that line y equals x. So my force in this case, since remember we had yi plus xj, that would be the same then as t, if I want to write it in terms of my parameter. Okay, and also my path here is also going to be t. And the derivative of that path would be 1, 1. Okay, so now for this line integral, I'm going to do my f dot dr. And in this case, that's the same as the integral from 0 to 1 of t dotted with, I forgot my prime there, with my r prime 1, 1 dt. So I'm just doing a dot product to evaluate that. That ends up giving me an integral from 0 to 1 of 2t dt. And we get a value of 1. So, we're talking about work, so maybe 1 joule. Okay, so the idea here, though, is regardless of the path that I take, I should be getting that same work value every single time that I run this calculation. So let's try this on a different path. So now we're going to look at the parabola y equals x squared. So we're going to have a little bit different parametric definition here. So I'm going to use x is equal to t. That means y would be equal to t squared this time. So for my force function this time, remember this vector was yx. So the y is t squared and the x is t. And this time for my position, the derivative of my position, I'm just taking the derivative of t and t squared. I'm going to end up with 1, 2t. Okay, so now let's look at this integral. So now I'm going to do the same integral on this curve C, f dot dr. And in this case, we're going to integrate from 0 to 1. And when I do my dot product here, I'm going to get t squared plus 2t squared. So that's going to give me 3t squared dt. And when I solve that out, I'll get t cubed over 3 evaluated from 0 to 1, gives me a value of 1. Okay, so we were suspecting that we have independence of path. It now is appearing that we have independence of path because you can see that we got the same work value for each of those calculations, and we took a very different path. This one we went along y equals x for part A. This one we went along y equals x squared. Let's try one other path. Let's say we went along this cubic path. Well, it's the same idea again. Along this cubic path, I would say my x is equal to t, my y is equal to t cubed. And so for my force function this time, I'm going to have t cubed t because it was yx. And then for the derivative of my position, I'm going to end up with 1, 3t squared. And now when I evaluate this integral, f dot dr, remember we've got to do that dot product. The dot product in this case, I know I'm going to integrate from 0 to 1, but the dot product in this case is going to give me t cubed plus 3t cubed. So I'm going to get 4t cubed dt. And obviously, when I solve that out, I'll get t to the fourth, evaluated from 0 to 1, gives me a value of 1. Okay, so you can see we apparently have independence of path here. Okay, so not that difficult to do, but the main idea is this whole idea of independence of path is something that we're going to want to try to figure out. How do we actually sort of know when we have this independence of path? Okay, so the way that we can check to see whether or not we have independence of path is actually to figure out if we have what we call a conservative vector field. So when we talk about a conservative vector field, what we're talking about is, let's say we've got two functions that are continuous and have continuous first partial derivatives. And if that's the case, and they are the components of my vector field, then I have to check to see if this is true. Del f del y has to be equal to del g del x. So we're looking at the partial derivatives. If I take the partial derivative of the I component and it's equal to the partial derivative of with respect to y of the I component, and it's equal to the partial derivative with respect to x of the j component, that would mean I have a conservative vector field, which would also then indicate that I have independence of path. Okay, so the way that I can check this then is fairly simple. So let's take a look at this problem. So it says determine whether this vector field y plus xi plus y minus xj is conservative on some open set. Okay, so the way that I can check, in this case, my f function is always the I component. It's y plus x. My g function is the j component, and it's xy here, and it would be y minus x. And if I look at del f del y, I get 1. If I look at del g del x, I'm going to get -1. So that means that our vector field is not conservative. Okay, so that would also indicate to us that we don't have independence of path. Okay, so that's the check that we can do to easily figure out whether or not we're going to have this whole idea of independence of path. We usually use this with this idea of testing for a conservative vector field. Now we're doing a really simplified version of a conservative vector field. Okay, so this is all going to depend on whether we have what's called a simply connected region. And a simply connected region is like something like this, where I've got a region that is essentially a region that if I were to collapse it down upon itself, it would collapse into a point. An example of something that's not a simply connected region would be like, let's say I have a region like this, but it's got, maybe a hole in the center of it, some kind of part in there where our domain is restricted from that. So now I can't collapse down into a point. So what we're assuming when we look at our simple definition for a conservative vector field, all we're looking at are these simply connected regions. So a lot of this is starting to get into things that we're not quite going to get into the applications of, but it's just a slight extension on what we're going to do here with fundamental theorem for line integrals. Okay, so let's take a look at an example here. It says, let's let this force field e to the yi plus x e to the yj be in the xy plane. Verify that this force field is conservative to start with. And then what we're going to do is we're going to find the work done by the force field on a particle that moves from one point to another on a semicircular path. Okay, so let's take a look at the first part of this. Let's check whether or not this is conservative. So if this is going to be conservative, then remember we need to check this. F of xy is equal to e to the y. G of xy is equal to x e to the y. And then I want to do del f del y, and I'd get e to the y. I'd want to do del g del x, and I would get e to the y again. So usually you can kind of check that in your head. This one, they wanted us to actually show it. So we have verified this. So we can say, therefore, our vector field is conservative for all points in the xy plane. Okay, so now that we have verified that it's conservative, we know we have independence of path, but what they asked us to do here was find the work done on a particle that moves from 1, 0 to negative 1, 0 along this semicircular path that's shown in this region. Okay, so remember, if I have independence of path, it doesn't matter if I follow that semicircular path or not. The only thing that matters is where did I start and where do I finish. So the amount of work that it's going to take here, we know we're going to go along our curve and we're going to do the dot product of f dr. Okay, so now let's choose the easiest path, right? The easiest path would be a straight line from 1, 0 to negative 1, 0. So that's what we're going to end up doing here. But before we do that, remember when we first looked at this, we had this force field, and we knew that if we look at the first piece of it, the force field was e to the y I. So whatever my original function was, so I'm kind of thinking about an antiderivative here. If I took that original function and took the partial derivative with respect to x, that was the I component. I got e to the y, right? That's what was given. The original function with the derivative taken with respect to y, a partial derivative with respect to y, gave me the result of x e to the y. So from that, what I'm trying to do is I'm trying to figure out what was the original function. Okay, so the last part of this is just a little bit tricky because remember, we started at the point 1, 0 and we ended at the point negative 1, 0. So when you're thinking about a lower and an upper value in terms of limits of integration, the lower limit of integration here is essentially what's happening at the point 1, 0, and the upper limit's what's happening at the point negative 1, 0, because that's the finishing point. So when I do my work calculation here, I'm going to use this phi function, but I'm going to evaluate at negative 1, 0, because that's the finishing point, minus that phi function at the original point of 1, 0. And when I plug that in, I'm going to end up with, let's see, I'll get negative 1 e to the 0 minus 1 e to the 0, and I end up with negative 2. So you can see that in the end here, the work calculation gave me a negative value, and that's primarily because if you look at the vectors in relation to the path that I took, I'm going in the opposite direction of the vector field as sort of a general rule there. Okay, so a lot of this, as you go through the problems in this section, are going to involve work calculations, but we're really just getting into kind of the main idea of the fundamental theorem of line integrals, and the way that we're displaying that is by doing the work calculations.